Welcome to AI Paper Podcasts. This is where we take a deep dive into the latest research, pull out the key insights, and really boil it down to what you need to know.
Yep, cutting through the noise.
Exactly. And today we're tackling, well, a really fundamental challenge in AI, especially if you're building or working with large language models.
Would you?
How do we get these LLMs to genuinely understand what we want, to reason properly, follow instructions, and give us the outputs we actually need? It's often a bit of a struggle, feels like a black box sometimes.
Definitely a core problem.
So we're looking at a really interesting new paper today. It's called Supervised Fine-tuning on Curated Data is Reinforcement Learning and Can Be Improved by Chongli Chin and Just Tobias Springenberg.
Quite a title.
It is. Now, for the quick overview, the sort of 1-minute version you can share, the core idea here is that supervised fine-tuning, SFT, that technique everyone uses, it looks simple.
Right, standard stuff.
But they argue it's not just basic training, it's actually optimizing a lower bound of the reinforcement learning objective, RL.
Okay, that's a big claim. Because RL, well, it's powerful for aligning models, getting them to reason.
Super powerful. But it's also notoriously tricky, right? Hard to interpret, hard to tune, unstable sometimes.
Exactly. Whereas SFT is, the reliable workhorse, stable, simple.
So this paper explains why SFT works surprisingly well for things like reasoning, and it shows how to make it better.
And that better part is their proposed solution, importance-weighted supervised fine-tuning, or IWSFT.
Right. Tell us about that quickly.
It's basically a small tweak to the standard SFT process. You reweight the data examples using an auxiliary distribution. Sounds technical, but the key is it tightens that connection back to the true RL objective.
Making SFT more effective at achieving those RL-like goals.
Precisely. More bang for your SFT buck, essentially.
And the results seem pretty compelling. They show iw-SFT significantly boosts reasoning on benchmarks like AIME 2024. What was the number?
Yeah, they hit 66.7% on ANA, which is a noticeable jump from standard SFT results. And it's competitive in offline RL control tasks, too.
Showing it's not just an LLM thing. Plus, and this is great for engineers, they say it's easy to implement.
That's a huge plus.
And maybe the kicker, it might even remove the need for things like budget forcing at inference time.
Yeah, that inference time compute saving could be really significant.
So our mission today is to really unpack this. How is SFT actually RL? Why does the standard approach fall short? And how does IWSFT give us this simple but powerful boost?
We'll dig into the surprising connections and what it means if you're training these models. Let's get into it.
Okay, so we have these massive LLMs trained on like half the internet, but getting them to do specific, useful things, that's the post-training challenge, right? Especially for reasoning or reliable instruction following.
Absolutely. That post-training phase is critical. And for a while, reinforcement learning, especially RLHF or RLAIF, getting feedback from humans or other AIs, that's been seen as the gold standard for alignment.
You see it in models known for reasoning, like DeepSeek R1 or OpenAI's O1, right? They lean heavily on RL.
Exactly. RL is undeniably key for pushing those sophisticated reasoning abilities.
But you mentioned earlier, if it's the gold standard, why isn't everyone just using RL all the time? What are the practical hurdles?
Well, that's the rub, isn't it? RL is just hard. It's difficult to interpret what's going on under the hood. Tuning the hyperparameters can feel like alchemy, and it often demands huge amounts of compute and data.
Like wrestling that black box we talked about.
Pretty much. And that's why you see so much work trying to make RL more stable, or methods like DPO, direct preference optimization, trying to get similar alignment results without the full complexity of explicit RL training.
Okay, so RL is powerful but complex. Then what about SFT? How does that fit in?
Well, what's been really interesting is seeing recent work showing that you can actually get surprisingly good reasoning improvements just by doing straightforward supervised fine-tuning, but only on carefully filtered or curated data sets.
Just picking the good examples.
Kind of, yeah. And SFT is stable, it's simpler, everyone knows how to do it. So the big question this paper tackles is, why does this simple SFT on curated data work so well for complex tasks like reasoning? Seems like it shouldn't, without the explicit reward optimization of RL.
And this is where their core insight comes in the idea that SFT is actually optimizing a lower bound of the RL objective. They connect it back to existing ideas, right? Like RL as inference.
Exactly. They build on that literature connecting RL to inference problems and also to iterative maximum likelihood learning, which is basically what SFT is.
So what's the aha moment? How does filtering data suddenly become RL?
The key insight is that when you filter your data, say, keeping only the successful reasoning traces or the high reward trajectories that act of filtering implicitly functions like a sparse reward signal in an RL framework.
What sparse mean?
Meaning you're essentially giving a reward of 1 to the data you keep. Good stuff. And 0 to the data you discard. It's a binary reward. And when you perform SFT on that filtered data set, the math shows you're maximizing a lower bound on the expected return you'd want in a proper RL setting with that same implicit reward.
Okay, let's try to get the intuition without diving too deep into the math equations. The RL goal is like maximizing the total expected future reward, right? Find the best possible path.
Right. Maximize expected return.
Yeah, and they use some kind of mathematical relationship and inequality.
Yeah, a well-known one. Basically relating a value to its logarithm. X equals 1 plus log x.
Yeah.
They apply this to the importance weights in the RL objective.
Importance weights being how likely the good action was under the original data generating policy versus the current learning policy.
Sort of, yeah. By applying that inequality, the complex RL objective can be shown to be at least as large as another term. And that other term looks remarkably similar to the standard SFT objective when you assume that sparse binary reward from filtering.
Wow. Okay, so SFT on filtered data isn't just analogous to RL, it's mathematically optimizing a simplified version or a lower limit of the same goal.
That's a good way to put it. It explains why SFT can work surprisingly well, but also hints at why it might not reach the true optimum because it's optimizing a bound, not the thing itself.
And they extend this. What if you have more than just good or bad data?
Right. If you have finer-grained quality scores, maybe ordinal classes like poor, okay, great, you can do what they call SFTQ. Here, you sample the data for fine-tuning proportionally to these quality scores.
So you focus more on the great examples than the okay ones.
Exactly. And mathematically, this SFTQ optimizes a tighter lower bound on the RL objective compared to just using binary filtered data. So it should, in theory, perform better.
But there's still a catch, right? You mentioned a flaw with both standard SFT and SFTQ.
Yes, this is crucial. Both of these SFT approaches optimize bounds, but these bounds become looser, less representative of the true RL objective, as the fine-tuned model's policy drifts further away from the original policy that's generated the data.
So as your model gets better and learns to behave differently from the initial data source, the connection guiding its learning gets weaker.
Precisely. The map gets blurrier, as you put it earlier. The SFT objective becomes less aligned with the actual RL goal you implicitly started aiming for. You need a way to keep that connection tight.
And that's where IWSFT comes in, to tighten that bound.
Exactly.
Importance Weighted Supervised Fine-tuning, IWSFT. The core idea is actually quite elegant. They introduce a small modification to the SFT loss function.
What's the modification?
They introduce an auxiliary distribution. Let's call it Q. You can think of this Q as representing the model's current best guess or policy direction.
Okay.
And they use this Q to calculate importance weights for each data point in your curated batch. Essentially, data points that are more likely under your current policy Q, compared to the original data generating policy, get higher weights in the SFT loss.
So it adaptively focuses the training on the examples that seem most relevant or preferred according to where the model is currently heading. That's the intuition. It puts more emphasis on the good data that aligns with the improving policy. And here's the kicker. As this auxiliary distribution Q gets closer to the actual policy P that you are optimizing, the lower bound on the RL objective tightens.
So if the map stays clearer, the guidance becomes more accurate as the model learns.
Exactly. It maintains a stronger connection to the true RL objective throughout training, leading to potentially much better optimization compared to standard SFT, where the bound just gets looser.
Now, importance weighting can sometimes introduce variance problems, right? Wildly fluctuating weights.
That's a valid concern and a common issue in RL methods using importance sampling. But the authors point out that they have control over this auxiliary distribution Q. They can manage the variance, for instance, by clipping or smoothing the importance weights.
How do they choose Q in practice?
They use a time-lagged version of the policy parameters being optimized. So Q tracks the main policy P, but slightly delayed, which helps with stability.
And you mentioned it's easy to implement.
Relatively speaking, yes. Compared to setting up a full RL pipeline, it mainly requires having an extra reference model, loaded potentially the original SFT model or the data generating model, to compute the likelihoods needed for the important weights on the fly during training.
So a bit more memory maybe, but conceptually straightforward if you're already doing SFT.
Pretty much. A small code change for potentially significant gains.
Okay, let's make this concrete. You mentioned the Bandit problem example. Walk us through that again, highlighting the difference.
Sure. Simple scenario. 2 slot machines, 2 arms. Pull left gives a reward of 1, but only 50% of the time. Average 0.5 reward. Pull right always gives a reward of 1. Clearly, always pulling right is optimal.
Got it.
Now, imagine your initial data comes from a policy that just pulls randomly, 50-50 left or right. You collect a bunch of attempts.
Okay.
If you do standard SFT on curated data, meaning you filter only for the pulls that resulted in a reward of 1, what happens?
Well, you keep all the successful pull right actions and only half of the pull left actions, the ones that happen to pay out. So your curated data set has twice as many pull right examples as pull left.
Exactly. Now, if you train an SFT model on that data set, it learns to mimic the proportions. It ends up with a policy that pulls right 2/3 of the time and left 1/3 of the time.
Which gives an average reward of 23.1 plus 13.0.5 equals 46 plus 16 equals 56. Better than random, which was 0.75, but not optimal, which is 1.
Precisely. It's suboptimal. And the core reason is that standard SFT, by filtering, completely throws away the information from the failed pull left actions where the reward was low. It literally cannot learn from those failures.
That seems like a huge blind spot.
It is. That's the Achilles heel of basic SFT on curated data for these kinds of optimization problems. It doesn't use all the information.
So how does IWSFT fix this in the Bandit example?
IWSFT, by using the importance weights, doesn't just discard the failures in the same way. It adaptively increases the weight on the pull right actions as the policy learns they are better. It effectively learns to value the successful pull right actions more relative to the successful pull left actions, even considering the implicit failure rate of the left arm.
So it uses the relative success rates, informed by the importance weighting, to figure out the truly optimal action.
Essentially, yes. The importance weighting allows it to more accurately estimate the expected value and push the policy towards the truly optimal strategy, always pull right, which standard SFT couldn't reach from the curated data alone.
That's a much clearer picture. It really highlights how IWSFT extracts more signal from the same underlying data.
But again, with the caveat, you need to manage those weights. Unbounded weights could cause instability. So clipping or smoothing, as they do in the paper, is important for making it work robustly.
Okay, that makes sense. Now let's move from toy examples to the real deal. What about the LLM reasoning results? Those sounded impressive.
They really are quite compelling. They took an open model, Qwen 2.532b Instruct, and fine-tuned it using a dataset called S1.1K.
What's special about S1.1K?
It's a curated set of about 1,000 high-quality reasoning traces. Importantly, it was carefully decontaminated against benchmarks and filtered for both quality and diversity, so good quality input data.
And they tested this on
tough reasoning benchmarks. AIME 2024 math competition problems, Math 500, and GPQA Diamond graduate level questions.
And the headline result? IWSFT versus standard SFT.
IWSFT, especially the version using full sequence importance weighting, showed significant gains. On AIME 2024, it hit 66.7%, whereas the standard SFT variants were in the 50% to 56.7% range. That's a big jump.
Wow. What about the others?
Similar story on GBQA Diamond, 64.1% for IWSFT versus around 56.6% to 63.6% for standard SFT. On Math 500, the performance was similar, but the trend across the challenging reasoning tasks was clearly in favor of IWSFT.
That's solid evidence, and you mentioned the budget forcing aspect earlier.
Yes, and this I think is one of the most surprising and potentially impactful findings. Usually, to get top reasoning performance, especially on complex problems, people use techniques like budget forcing at inference time.
Which is basically making the model generate more intermediate steps, use more compute, right? Injecting weight tokens or similar tricks.
Exactly. It forces more thinking time. But the IWSFT model achieved its peak performance without needing budget forcing.
So the improvement seems to come from better training, making the model inherently more capable rather than needing an inference time crutch.
That's what it suggests, that IWSFT is extracting more value, more signal from the training data itself, leading to a more efficient and powerful model without needing extra inference compute. That's a potential game changer for deployment.
Setting a new state-of-the-art for open models on open data, you said.
Yes. Based on their comparisons, it looks like a new soda in that category. Of course, powerful closed models might still be ahead, but it's a significant step for open approaches.
Okay, and it wasn't just LLMs. They also tested this on robotic control tasks, offline RL.
Right, which really speaks to the generality of the underlying principle. They use standard offline RL benchmarks from D4RL tasks, like controlling simulated robots, have Cheetah, Hopper, Walker to Tekken, using pre-recorded datasets.
Datasets with varying quality, like expert demonstrations versus medium replay data.
Exactly. And here, they curated the data differently. They took the top 10% of trajectories based on cumulative reward, and then binned these rewards into 3 overlapping quality classes like good, better, best.
So they could use the SFTQ and IWSFTQ variants, leveraging those quality scores.
Precisely. And the results were consistent with the theory. First, SFTQ, just using the quality scores, clearly beat standard behavior cloning, which just mimics the data, and also standard SFT, which would use binary filtering. So using quality scores helps.
Okay, and then IWSFTQ.
IWSFTQ provided a further, albeit smaller, improvement over SFTQ in these control tasks. It wasn't as dramatic as the LLM reasoning gains, perhaps, but it consistently showed a benefit.
And how did these SFT-based methods stack up against established offline RL algorithms?
Impressively well. They were competitive with strong baselines like AWAC, TD3 plus BC, CQL, and IQL, which is remarkable, really, for what is fundamentally a modified supervised learning approach competing in an RL domain.
Did they try any other control tasks?
Yes. They also used the Franca Kitchen environment, which is known for having more diverse, less structured data and potentially noisy quality signals. Even there, IWSFTQ showed it could effectively recover performance, closing the gap compared to training on less complete or lower quality datasets. It shows robustness.
So the core idea, tightening the RL bound via importance weighting in SFT, seems to hold up across very different domains: LLM reasoning and continuous control.
It really does seem quite general.
Of course, no research is perfect. What limitations did the authors mention?
They were quite upfront. They noted that the improvements, while significant, were primarily demonstrated in relatively narrow domains. For LLMs, it was focused on reasoning. They suggest more extensive evaluations are needed across a broader range of tasks to really map out the full scope of where IWSFT excels.
Makes sense. Anything else?
They also acknowledge that while IWSFT often improves significantly upon SFT, it doesn't necessarily bridge the gap to the very best existing models in all scenarios, especially when compared perhaps to highly optimized large-scale RLHF pipelines or closed models. So there's still room for improvement in research, maybe looking deeper into data curation strategies or combining IWSFT with other techniques.
And it's worth mentioning maybe the ethical dimension. Better alignment is good, but...
That's a crucial point they raise. While the goal here is better alignment with desired behaviors, like good reasoning, the same technique could potentially be used with adversarially curated data to create models aligned with harmful objectives. Improving alignment methods also means we need to be vigilant about how those methods could be misused.
Absolutely, a really important consideration. Okay, so let's try and synthesize this. What's the big takeaway for people listening, especially those working with LLMs or control policies?
I think the fundamental takeaway is this reframing of SFT. If you're doing SFT on carefully curated data, you're already doing a form of RL optimization, whether you realized it or not. You're optimizing a lower bound.
And knowing that allows you to improve it.
Exactly. IW-SFT provides a concrete, relatively simple way to improve that optimization, to tighten the bound and get closer to the true RL objective, extracting more value from your curated data.
So, practically speaking, if you have a curated data set you're using for SFT,
you should consider trying IW-SFT. It's presented as easy to implement, requiring that extra reference model for weights, and the potential payoff in performance, especially for reasoning or complex control, seems significant based on these results.
Plus the potential bonus of maybe not needing hacks like budget forcing.
Right. Potentially better performance and more efficient inference. It's about making your supervised fine-tuning more powerful by leveraging this connection to RL.
It really does blur the lines between supervised learning and reinforcement learning, doesn't it?
It does. It makes you wonder, if we get really good at data curation, at defining what good data looks like, and combine that with sophisticated weighting schemes like IW-SFT,
could we achieve most of the goals of complex RL pipelines primarily through these enhanced supervised learning methods?
It's a fascinating question, isn't it?
Yeah.
Could this dramatically simplify how we approach alignment and capability development in the future?
Yeah.
Making these advanced techniques more accessible, it certainly opens up some intriguing possibilities for where the field might go next.
A lot to think about there. Definitely a paper worth digging into if you're in this space.
Absolutely. Thanks for diving deep with us today.
Until next time on AI Paper Podcasts.